10.68. Now, the new thing on 10.68 is that now on top of what we had before, we're also going to have cogeneration. Okay, so we have regeneration like before, and now we're going to have cogeneration happen. So it's two different things. You guys are going to love it. So consider a power plant with modified with a cogeneration power plant with modified regeneration. Steam enters the turbine at 9 megapascals and 400 C, so that's our upper limit, and expands to a pressure of 1.6 megapascals. At this pressure, 35% of the steam is extracted from the turbine, and the remainder expands to 10 kilopascals. So it's pretty much giving us Y. Yeah, so it's giving us the Y that we just had to find in the previous one. This one, they're giving it straight off. Right? So the remainder of that is the 65% goes through a second turbine and ends up at 10 kilopascals. Part of the extracted steam is used to heat the feed water in an open feed water heater. The rest of the extracted steam is used to process the heating, for process heating, and leaves the process heater as a saturated liquid at 1.6 megapascals. It subsequently mixed with feed water, leaving the feed water heater, and the mixture is pumped to the boiler pressure. Assuming the pumps and the turbines to be isentropic, thank God, we are to show the process on a TS diagram with respect to saturation lines, and we also need to determine the mass flow rate of steam through the boiler for a net output of 25 megawatts. Okay, the hardest thing on this one is not the solving of it. You'll see the solving is quite similar to the previous one. The hardest thing is making sense of all this text, what the hell they're talking about. Okay, so I want you guys to pay attention to as I explain what this means, what's being said. I also want you guys to ask if you're in doubt or if you don't understand. Right? It's best to ask now than to go into this question being completely lost. So let's do what this is. I'm going to start with the things that we have. We're going to have a pump like before. That's not going to change. We have the pump down here. Now we're going to have our open feed water heater. And we have the mixing chamber like before. This didn't change. Still going to have a second pump like before. Nothing has changed in this regard. Still have the boiler over here. We still have the turbine. But now what happens is we break this steam coming out of the turbine into several condenser. Okay, and then we're going to have the process heater, which is the neat thing. Let me do my little blocks around these. Okay, so the basic process is still the same, right? We start with, we'd start over here. That will be our state one. And we have saturated liquid. I'm going to pump that in. That's going to go through a open feed water heater, which is going to go afterwards into a chamber. And that's going to mix up things coming from different places. And in this case here, we're going to have the second pump. It's going to make sure that our state here is compressed before going to the boiler. The boiler is going to ensure that we have steam coming out of this, which is going to go through the turbine. Now on the turbine, and this is the new part, okay, part of it is going to go through that second turbine over there. So I should probably draw the second one here. Turbine 2. Okay, so part of this is going to go through this second turbine over here. But another part is going to be split between the process heater and the open feed water heater. So the process, so let's do this in different colors so that's we're all on the same page of what's happening. And this guy's going to be my red. Okay, so let's talk about what's happening here. We, like before, we have a open feed water heater, and the idea of this is, again, since I still have some quality to the energy that's leaving the turbine, instead of rejecting that in the condenser, I can use that to my advantage to actually, instead of having to go all the way from down this state of energy, all the way up here again, I can just start from halfway and use less energy in the process, right? So that's the open feed water heater. So that didn't change in respect to the previous one. That's the red line here. Now, the process heater, that's the new thing. The process heater, the idea is the following. Think that we have a process, we have a power plant, that's running this cycle, and next to the power plant we have another plant. It can be a chemical plant. Chemical is probably the best example because they use this in real life. And this chemical plant has their chambers, and in their chambers they have chemical HX, and transforming that into HXZY. Okay, this chemical process can be creation of polymer formation. This can be any sort of reaction that occurs, but this guy occurs at 300 Celsius. I'm making up numbers. Now, if I have this company and I need to do this process, I can heat this guy up with fire down here and actually heat it up with coal. So I can put coal into here, or I can use electricity to heat this up. Okay, but all these things are going to cost me a lot of energy. Okay, so if I'm doing this, and I'm going to input a lot of energy here, so much so that it might be worth building a power plant, either combined with my one, or just make a partnership with somebody of a company that operates power plants to build one right next to my system. So once that hot water leaves the turbine, right, which is this guy here, right, this point here, I can have pipes that are going to go through my system, and the water is just going through, right? It's not touching the chemical or anything like that. It's just going through that, so that I can increase the temperature on this guy here, right? So I can take this guy to 300 Celsius. And then afterwards, since the water didn't touch, it's just normal water, I can put this back into my normal cycle. So if I have a chemical plant right next to my power plant, I can take advantage of the quality of the energy that's leaving the turbine to run my process. And as a bonus, I can also have the energy generation that this turbine is giving out and that this turbine is giving out. Okay, so that's the idea of having the process heater. I'll do another analogy that I found helpful, which is, picture you're cooking an egg. Okay, you're cooking an egg at home and you're boiling the water in a pan, and the water starts boiling and you put the egg in. So you just heated all that water to be able to cook that egg. But it's also a cold day, so you put your hand on top of the pan and you get that little steam coming into your hands and warming up your hand. It's kind of the same idea, right? That steam would come out and would be rejected. We wouldn't use that. It wouldn't be useful for us to cook the egg. But if I put my hand, it's like putting one of these boxes here and there, and I'm also using that energy to something else. My analogy, to warm up my hands, in this case here, to make this reaction occur. Okay, so that's the idea behind using one of these process heat. In terms of TS diagram, it's not as complicated as it looks, because if you think about it, let's check out. We have state 1 down here, and we're going to increase the pressure, so we're going to have a state 2 in between these two guys here. Then we have the open feed water heater receiving energy, so that's going to be our state 3 over here after the heater. But the pressure from it and the pressure from the process heater is going to be the same. I'm going to go ahead and put this 9 here, okay? And after it goes through the mix, that will be our state 4. But check out, state 3, 4, and 9 are the same, because on the mixing chamber, nothing changes. It's not like we're putting more energy into there, or that we're putting more pressure, or that we're doing anything like that. No, it's just a place in which the water coming from the open feed water heater is mixing up with the water coming from the process heater. And it's all the same temperature, all the same pressure, so it's all the same properties. After it leaves this mixing chamber, it goes through the second pump, and then we're going to have another state because we just increased the pressure. And after the boiler, we're going to have another state because we just made it all steam, right? And then once we leave our turbine, then we're going to have state 7, which is steam leaving the turbine over here. And just before this since we go through another turbine over here, we're going to have another state here. 8.
You just did 2 state 7s, like the one beside turbine 1 and the one below turbine 1.
Oh, I did. That's right. Thank you. So this is 6. Thank you.
Of course.
Thanks. Yeah, there you go. So 6, then 7 after the first turbine, 8 after the second turbine, right? And then our 9 would be the one leaving the process, this process heater, and then jumping back into our mixing chamber there. Okay, now this is what's happening like in real life. This is what the layout diagram of this cogeneration and regeneration cycle would be. Okay, now why is it cogeneration? Because I'm literally generating 2 things in one process. I'm generating, let's do yellow. I'm generating electricity, right? I mean, I'm assuming it's electricity out of these 2 turbines. And at the same time, I'm generating energy for this process to work. So that's why it's cogeneration, right? 2 generations. The electricity on the turbines, the mechanical energy here, and the one for the process heat. Okay, and why is it also with regeneration? Because we also have this fella here, which is taking part of that energy. Whew, I know it's a lot, but stop me if you get lost, and I'm happy to repeat everything.
Can you explain what the difference between the red line and the blue line? I'm kind of lost.
The red line?
Yeah.
What's the other one?
And the blue one.
The blue one. The red line, this red line here is when the steam leaves the turbine and it goes to the feed water heater. So this guy here, oops, that was supposed to be the highlighter. This guy here is the same idea as before. The reason why we have this red line is so that part of that energy that would otherwise be discarded because it's not useful for the process heat and it's not useful for the turbine 2, we would just condense it. Instead of having that energy rejected, we just putting it back into our system. So we save ourselves some energy and increase the efficiency of this process. So this is the same idea. The red one is the same idea as the previous one. Okay, exactly the same idea as the previous one. The new thing on this problem is this guy here that we didn't have before. Let me do this. If I take away this is exactly what we had on the previous problem.
Yes.
Yes, and then I'm putting that process heater over there. So now I also have on top of my open feed water, I also have the process heat, which is this guy here. This guy here. So it's 2 completely different things. One, I'm taking advantage of the energy to do a reaction, to do a process on a chemical plant or a neighboring plant, this guy. And on the other one, I'm just taking advantage of the energy that I would otherwise discard and putting it back to my own cycle.
Right.
Okay, so I'll draw the TS diagram for us now. And I know it looks messy, but it's not. The TS diagram is not as bad as this. Okay. The other thing that we know before I go to the TS diagram, the other thing that we know is that Y, and I'm going to read off the problem statement here. 35% of steam is extracted from the turbine, and the remainder expands to 10 kilopascals. Okay. So what we're saying here is, I'm going to redraw this first turbine down here so it's not overwhelming, right? So we have turbine 1 here, turbine 1, and then turbine 1 is going to have 3 outputs: the red one, the blue one, the red one, and the black one. Okay, well that statement is saying, I'm going to read it again for you guys. 35% of steam is extracted from the turbine, and the remainder expands to 10 kilopascals. Okay, so we know that this guy here is a reminder. This is the one that's going to expand 1 minus y, which in this case is 1 minus 35, right? 1 minus 0.35. Okay, so we know 65% goes into the second turbine, turbine 2. And we know that 35% go into these 2 guys here. I don't know whether it's 10% for one, 25% for the other one. I have no idea what's the split between these 2. All I know is that once it leaves turbine 1, 35% goes to these two guys here, and 65% goes to this guy here. Okay, so let's look at our TS diagram. I might take advantage of this line here. Okay, my state 1, like before, nothing changes, and then I go up to state 2. State 2, I have the open feed water heater, and I end up at state 3. I'm going to compress state 3 and then go to state 4. State 4, I'm going to have the boiler kicking in and heating up this water all the way to 5. It's not 5 anymore, it's 6. Then I'm going to drop. Part of it's going to drop all the way down with the turbine 2, all the way here, and part of it's going to go this way. Okay, so in terms of TS diagram, it's very similar to what we had before. Let's put the states that we have. State 1, state 2. Then state 3 and 4, right? Because it doesn't really change, if you guys recall. All we have here is the mixing chamber, so it doesn't really change. 3 and 4 are both there. Then we're going to use a second pump to go to state 5, state 6 before the turbine, and then it leaves the turbine and leaves at state 7. And then on state 7 is where we have the split. Half of it, not half, 35% goes this way into the open, the feed water heater and the process heater. I'm not sure how much for each. And we know that the reminder that's the 65% goes down here to our 8. And then finally we have our 9, which is over here. Okay, so in terms of TS diagram, it's pretty much the same as the previous one. Okay, we have 9 states instead of 8. I think we had 8 before, or 7 we had before, but 3 of them are the same. So in terms of solving, it's going to be pretty much the same thing for us. Okay, what am I going to do? I'm going to do the solving of every single state like before, so that I can find the mass flow rate that I need through the sky. Again, like before, we need to pay attention that we have Qin going from 5 to 6, and that's taking up 100% of the mass flow rate. And I have my heat rejection here from 8 to 1 out. But this only uses, I'm going to put a little star here, this only uses 65% of the mass, right? Not all of it. So we need to take that into account. We have, in terms of solving the states, I'm going to be really fast solving this because there's nothing new, right? We have pressure and saturated liquid here. Oh yeah, let me draw the dome since we're here. Why not? Let's draw the dome in blue, I guess. No, green. Okay, so we know first one is saturated liquid. You also know the second one is saturated liquid because it leaves the process as saturated liquid. It's going to go like so, and theoretically, it's going to go like so. Okay, that's our dome right there. So again, going back, how we're going to solve this. 1, we have saturated liquid and the pressure, so it's done. From 1 to 2, we can do our savvy little trick with the specific volume. 3, specific saturated liquid, and we know the pressure, so it's done. And we can do the same process to 5. 6 is defined. We have pressure and temperature, and once we find 6, we have the entropy as well, which will be the same for 7 and 8. Okay, so it's going to be, the solving of this part is going to be exactly the same as the previous one. No need to panic. Okay, I'm going to go fairly fast on this. You can stop me if you get lost, but it's the same thing as we did on the previous one. What's the pressure? What is it? 1.6. Yeah, the 1.6. 10 to the third minus 20 to the 10. Go away. Sorry. Four is the same as 3, so this is 5. 5. 5 will be into 4. Is it 9 megapascals? It's done. We know temperature and we know temperature and pressure. 96%, 0.96. By the way, let me just give you guys a little quick tip. Okay, when you find this quality, right, of the first turbine, and then you go on to find the next quality, make sure that the next one is smaller, right? It has to be smaller. There's no other possibility, right? Thermodynamically, it would not be possible for us to have a higher quality because we're not giving any energy from after the turbine. But that's a good way to gauge whether you're doing the right thing or not. If you get the same one or higher, you did something wrong. Just check your units, check what the math. You probably just had a little mishap. With this, we can go ahead and calculate our enthalpy 7. And enthalpy 7 would be 2730. Not 2010. So this is the part that I'm saying. If you do this guy and this guy happens to be equal or greater, then you did something wrong. Here is 75.18%. This one indeed smaller. This one we have about 4% liquid, and this one we have about 25% liquid. So it's going to be a combination of both guys, and this is 19. 2.2. Okay, so this is state 8. Let's have a look at what we have. State 1 enthalpy is, oh, come on, go away. State 1 enthalpy is there. State 2 enthalpy is there. State 3 enthalpy is there. State 4 and 9 also the same enthalpy. State 5 enthalpy is there. State 6 enthalpy. State 7, state 8. Okay, so we have the enthalpy for all the states. And note that it wasn't much different from what we did before. Yeah, speak up. What's up? Is that a question? Okay. So what are we looking for? We're looking for what's the mass flow rate that we need on this system to be able to give us a output of 25 megawatts. Okay. What am I going to do to do that? Well, I'm going to find the net work output of this guy. And to do that, what I'm going to do is I'm going to relate the two things that are being inputted minus the thing that's being outputted. So let's just go back here. Let's look at these two guys here. So for this guy first, I have two outputs of this system, right? I have two outputs. I have these two guys outputting, these two turbines outputting energy. And I have two things that are consuming energy in my process. I have pump or the compressor 1, this guy here in the bottom. I also have this guy here on top. Okay, so as per usual, our work net is going to be the relationship between, let me get this out of the way. So our work net, we can relate that as the work of the turbines minus the work of the compressors, or Q in minus Q out, because it's a cycle, right? On this instance, I'm going to change it up a bit, turbine minus the compressor. So let's have a look. This first turbine here, turbine 1, it has 100% of the mass flow rate. The bottom one, the turbine, this one, it only has 65% of that. So we need to make sure we account for that. On the and then we do the compressors, the pumps together. Okay, so let's do cross this out here and then do what is the work net? Well, that's going to be turbine 1 plus turbine 2 minus the work of the I'll do pump 1 minus the work of pump 2. Okay, so let's first do the turbines. So turbines. So work of the turbines will be, so 1, that's when we go from state 6 to state 7, right? So that's going to be state 6 to state 7. And 2, that's when we go from state 7 to state 8. That's going to be state 7 to state 8. Now, we also have to account for the 1 minus y, which in our case here is going to be 0.65, right? 65%. So for the turbine here, I've got, so this, I'll just call out the things that I have. This is 3118. This is 2730, 2730, 1990.2, and then 1 and 0.35, right? So we have all the values that we need, and the work of the turbine equals 869.7. Okay, what about the compressors? What do we have for the compressors? On the compressor side, we have, look at the compressors. What do we have? We have going from 1 to 2, and we're going from 4 to 5, right? So we're going from 1 to 2, plus going from 5 to 5. Okay. Is this correct? Is there anything that I need to do? Can I move on? Do you guys agree? Anyone?
Are you asking us to calculate it right now?
No, I'm asking if you guys agree with this line of,
Yeah.
okay, because this is a very common mistake, okay? That's why I'm asking.
I thought the whole video lagged for a second because no one's talking.
No, I'm still here. I was just waiting for you guys to have a look at this. And I'm highlighting this especially because a lot of students do this one wrong. Okay, I'll show you why. Oh, actually, you guys can tell me why, but in the interest of saving us time.
Is it because the process heater you've got a mixture as well as from 4 to 5?
From 4 to 5? No, that's not why. The reason why is because it's exactly the same thing as this one here, right? So when we're going from, this is probably less overwhelming. When we're going from, get out of my way, from 5 to 6, that's fine, the whole water is in here. When we go through the first turbine, we have the whole water in here. Then when we go through the second turbine, from 7 to 8, we have the whole water, we have only 65% of that water. And then students usually, they not only get this, but they remember it. What they forget is that it's still 65% over here, which means it's still 65% over here. So from 1 to 2, it's also 65%. right? From 3 to 5, it's the 100% back again, mass flow rate of water. But from 1 to 2, we also need to take into account 1 minus y. Okay, for the same exact reason we were doing for the second turbine. Because they see it here, usually students see it here, and then they remember that, but then they forget it's the same mass flow rate that goes all the way back to 3, right? We can't create mass, right? So it has to be the same. So if we go back where we were, here we are. If we go back here, what I need to do is okay, now this is right. So watch out. This ends up being 9.62. Okay, so our net will be just the difference between these two guys here, just like we did before with the heat. It's going to be the 869.7 minus 9.62. That's pretty much just subtract 9, right? So it's going to be 850. So we get 860 kilojoules per kilogram as the output of this cycle. Okay, now finish off. That's the output of this cycle. So that means that if we want to know what's the mass flow rate, we just take the mass flow rate we want is for 25 megawatts. It's going to be 25 times 10 to the third kilowatts, which is a kilojoule per kilogram. Oops, per second. Per second. And I'm just going to divide that by what this guy outputs. So this guy outputs 860 kilojoules for every kilogram. Okay, with that, these guys go away. And I'm left only with kilograms per second. And I got 29.1. That is our final answer. That's the amount of water we need going through this system so that we can get an output of 25 megawatts under those conditions. Okay, so that means that through our pump through our boiler, through the first turbine, we have 29 kilograms per second of water going through. But then through the second turbine, the condenser and first pump, we only have about 10 kilograms of water going through, right? So we have, no, I lie, 65%. So it's about 20 kilograms of water going through turbine 2, condenser, and pump 1. Whilst at the same time for the feed water heater and the process heater, we have about 10 kilograms of water going through. Okay, so in terms of solving, it's pretty much very similar to what we had before. In terms of understanding, it's a bit more complicated. Any questions?
Does that mean we didn't need